You're about to learn a new math operation called absolute value, and the way you identify it is these two absolute value bars around the x. So I would pronounce this y equals the absolute value of x. For review's sake, you're used to squaring an x or square rooting an x or even multiplying in an equation. This is just going to be a new operation called absolute value. And before we get into graphing, let's just look at what it does with arithmetic. If I have the absolute value of negative 14, that's 14. If I have the absolute value of 12, that's 12. The absolute value of negative 4.7 is 4.7. You're probably noticing a pattern, and the pattern is this. The absolute value will convert anything that's negative into a positive value. But if the value is already positive, like positive 12, the outcome remains positive. So you could really sum it up by saying absolute value just ensures that the result is a positive result. So we're going to start by taking a look at the parent graph, the base absolute value function. And you could make a t-table, a chart, and plug in the 3, plug in the 2, plug in the negative 2. And when you do that, you would get this out, meaning if I plugged a negative 3 into here, I would get the absolute value of negative 3, which is positive 3. If I plugged a 2 in, it's already positive, so the outcome just remains positive 2. So what would that look like as a graph? The parent graph of the absolute value function, once I plotted those points, would just look like a V. So it's kind of like you're used to the parabola, except the two segments, the left and the right side, are linear and they're not curvy. So this is our parent graph for y equals absolute value of x. But if we go back up to the top and we take a look at this equation, this is a fancier form of our parent equation, and it has an a out in front, and this a is going to change the shape of our parent graph. It's going to either make it more narrow or more wide and open upward or downward. So let's take a look. In this example, f of x equals 4 absolute value of x. The 4 is acting as the a. So let's see what that does. If I took a 3 and plugged it in, absolute value of 3 is still 3, so 4 times 3 is 12. If I took a negative 2 and plugged it in for x, the absolute value of negative 2 is 2. The absolute value of negative 2 is positive 2, so 4 times positive 2 is 8. Notice that all my outcomes are positive. So what would the graph of this look like? After I plot those points, I get this graph for y equals 4 absolute value of x, and you'll notice that this is more narrow than the parent graph. The parent graph would have been wider like this, so apparently when the a is 4, my graph is more narrow. We'll keep that in mind. So here's another graph where the a in front of the absolute value of x is smaller than 1, it's a fraction, and it's also negative. If I took the time to plug in these different x values, for example, if I plugged in a negative 2, the absolute value makes it positive 2. Negative 1/4 times positive 2 gives me a negative 1/2. Now you might be saying we can't have negatives, but remember this part right here is going to be positive, but when I multiply it by this part here, a positive times a negative gives me those negatives. So what would this graph look like? In this case, the negative on my coefficient made the absolute value graph open downward. Remember, the parent graph would look like this, opening upward. So the negative made my new graph open downward. Also, because the a was smaller than 1, this made my graph much wider than the parent graph. So based on those graphs that we've seen compared to the parent graph, we realize that this a, this coefficient out in front, does something. So you can always go ahead and make a table and graph it to find out, but this is a shortcut if you can put this into your brain. When the coefficient a is greater than 1, they call it a vertical stretch, but to your eyes, the graph looks skinnier or more narrow. Think of taking the parent graph and stretching it vertically. When you stretch it vertically, it will get skinnier. When the a is less than 1, when it's a fraction less than 1, that's called vertically compressed, but our eyeballs would say, hey, that looks wider. Think of squashing the parent graph down vertically, it would get wider. So in this case, the negative will tell me it's opening downward. The 5 will tell me it is much more narrow. And just like we used to do with the quadratics, you can translate left, right, up, and down. So for example, if I saw absolute value of x plus 3, this will translate upward 3 units. This is like inside the parentheses when we had quadratics. So this goes against your intuition. This is 2 units to the right. That's your introduction to the absolute value function, and we'll do some exercises, and we'll also show you why in the world that would actually apply to the real world in class discussion.